Welcome to the Deep Dive. We're plunging into some really fundamental forces that shape our planet today. We're talking about stress and strain in Earth's crust. Basically, the hidden architects constantly messing with the ground beneath your feet.
Exactly. And our mission today is to unpack how these seemingly solid rocks respond to just immense, relentless forces. We'll look at how this creates everything from, huge mountain ranges to some pretty surprising geological events based on the sources we've both looked at.
Okay, so let's start with the basics. When we talk about Earth's crust, stress and strain are key. What are we actually talking about?
Right. So stress, geologically speaking, is just the force applied over a certain area of rock. And strain, that's simply the result how the rock changes shape, how it deforms because of that stress.
Got it. Force and deformation. Simple enough, but I bet there's more to it.
Oh, yeah. There are different types of stress. You've got confining stress, which is basically the weight of all the rock piled on top. Think deep underground. It squeezes things together.
Okay, like being in the bottom of a swimming pool, but with rock.
Sort of, yeah. It makes things harder to break down there. Then there's compression. That's a squeezing force pushing rocks together. Very common where tectonic plates collide, convergent boundaries.
Squeezing. So what's the opposite? Pulling apart.
Exactly. That's tension. It pulls rocks, stretches them, makes them thinner, or even break apart. You see this a lot at divergent boundaries where plates are moving away from each other.
Makes sense. Compression squishes, tension stretches. Is that it?
One more key type, shear stress. Imagine forces pushing parallel to a surface but in opposite directions, like sliding a deck of cards. This happens along transform boundaries. The San Andreas Fault in California. Classic example of shear stress at work.
Okay, confining, compression, tension, shear. Four main ways the Earth is pushing and pulling its own crust. So how do the rocks themselves respond? Does a rock always just break?
Good question. No, it really depends on the conditions. Temperature and pressure are huge factors. Rocks have basically three ways to react. First is elastic deformation. Think of a rubber band, you stretch it, it changes shape, but let go, and it snaps right back. Temporary change.
Okay, elastic, like a spring.
Exactly. Then there's plastic deformation. This is a permanent change. Like bending a metal spoon, it stays bent. The rock flows or changes shape without actually fracturing.
Like silly putty? Maybe.
Kinda, yeah. Especially deeper in the crust where it's hotter and under more pressure. Rocks there tend to deform plastically. They sort of flow over long time scales. But closer to the surface, or if the stress is applied really suddenly, rocks are more brittle. They reach a point and then snap. That's fracture.
So deeper down, it's more like sculpting. But near the surface, it's more like breaking things.
That's a good way to put it. And these different responses create the features we actually see on the surface.
Right, like folds and faults.
Precisely. When rocks undergo that plastic deformation, especially from compression, they often buckle and create folds. You get these wave-like structures. Upward arches are called anticlines, and the downward troughs are synclines. You see them all the time in mountain belts.
Okay, so folds are from bending. What about breaking? You mentioned faults.
Right. If a rock fractures, but the pieces on either side don't really move relative to each other, that's just called a joint, like cracks in pavement. But if there is movement along that fracture, then it's a fault. And the type of fault depends on how things moved.
Okay, so movement is the key difference between a joint and a fault.
Exactly. And you get different fault types. Dip-slip faults have vertical movement. If one block drops down relative to the other, usually due to tension, that's a normal fault. If one block is pushed up over the other, typically from compression, that's a reverse fault. If the angle is really shallow, we call it a thrust fault.
Up and down movement. What about side to side?
That's the other main category, strike-slip faults. Here, the movement is horizontal, parallel to the fault line, caused by that shear stress we talked about. Again, think San Andreas Fault, two huge plates grinding sideways past each other.
It's amazing how these basic mechanics build entire landscapes, mountains, for instance.
Absolutely. Mountain building, or orogeny, is a direct result. The Himalayas, they're still rising because the Indian plate is crashing into the Eurasian plate, massive compression, causing folding and thrust faulting. The Andes are different, formed by an oceanic plate sliding under a continental plate, what we call subduction. Still related to compression, but a different mechanism.
So mountains are the obvious slow burn result. But you mentioned surprising events, too.
Yeah, sometimes the effects are much more immediate and frankly weird. Take river reversals. During the huge New Madrid earthquakes back in 1811, 1812, the land tilted so violently that parts of the Mississippi River actually flowed backward for a short time.
The Mississippi, flowing backwards. Seriously.
Seriously. just temporarily, but it happened. Shows the scale of deformation. And there are other examples, some natural, some not. There was this bizarre incident in Louisiana, Lake Peigneur. An oil rig accidentally drilled into a salt mine beneath the lake. The whole lake drained into the mine like a giant bathtub drain. And the canal that normally flowed out of the lake reversed course, becoming a massive waterfall flowing in.
Wow, that's unexpected.
Definitely. And we've even done it intentionally. The Chicago River was engineered to flow backwards away from Lake Michigan to deal with pollution. So we can manipulate these things, too, to some extent.
Okay, this is all happening, these immense forces. How on earth do scientists actually measure this stuff? You can't just stick a ruler in a fault zone, can you?
Hey, not quite. It's tricky. One method is called overcoring. They drill a small hole, put a sensor inside to measure the rock, and then drill a larger circle around the first hole. This relieves the stress on that inner core of rock. By measuring how much that inner core expands or changes shape when the stress is removed, they can calculate what the original stress was.
Clever. Drilling around it to see how it relaxes.
Yeah. Another common tool is using strain gauges. These are tiny, sensitive devices glued directly onto rock surfaces. They can detect incredibly small changes in the rock's shape, minuscule amounts of stretching or squeezing, giving us real-time data on how the rock is deforming under stress.
So pulling this all together, what's the big takeaway for us?
Well, I think it's that the ground we stand on, which feels so solid and permanent, is actually incredibly dynamic. It's constantly being pushed, pulled, squeezed, and sheared by these immense forces. This leads to everything from slow mountain building over millions of years to sudden, dramatic events like earthquakes or even those weird river reversals.
It really changes how you think about the Earth. It's not static at all.
Not in the slightest. It's a living, breathing, constantly deforming system.
Okay, here's a final thought to leave you with. Given how dynamic the Earth's crust is and these examples of pretty wild events, what other geological surprises, things we might think are impossible now, could potentially happen in our lifetimes?